Okay, section 8.2, day 2 or part 2. We are going to talk about the finding the areas between curves still, but we are going to talk about integrating with respect to y. So sometimes there will be functions that are strictly to the left or right of another function, and in those instances sometimes it's easier to integrate with respect to y. Also, it's possible that you will be given a curve that cannot be turned into a function in terms of x. And then at that point you may need to integrate it with respect to y. So let's get started. This area right here is, we're calling it R, is bounded above by this curve, which is the square root of x, and below by the x-axis, so this here, and by this line, y equals x minus 2. Now, in this section, you need to be very careful, and actually in subsequent sections as well, you need to be very careful about what region you are trying to find the area of, or eventually, when we start rotating these around different axes, trying to find the solid. But the area is really important in getting the region right. Now, if you just go at this problem like we talked about in the part 1 of this lesson, if you just say, okay, well, I'll take the top function, which is this curve, and then I'll subtract away the line. If you do that, what you're going to end up including is this area down here. If you take top minus bottom, here's the top, all the way to the bottom, like that. Okay, so you're going to end up with extra area. Okay, so you can't do that. Or you can't, you can do it, but you'll be wrong, right? So we're trying to find this area here that's right there. So one way that we can approach this is we can break this into two parts. So we can notice that from 0 to right here, that's one area that is just strictly underneath the curve y equals square root of x. And so maybe we call that area A. Okay? And then here to here, that area, we'll call that area B, and that is going to be square root of x minus the line here, x minus 2. And so this is called partitioning, or finding the area using subregions. Okay, where you just find each piece. Or you break the region into parts and then you find the parts. So the area of part A is going to be just the integral from 0 to 2 of square root of x dx. The area of B is going to be equal to the integral from 2 to 4 of square root of x, so that's top function, minus x minus 2 dx. All right, and when you add those two integrals together, you get that the region is equal to 3 and 1/3. Okay? So that's one way to approach this problem. Another way to approach this, we hop down here. I'm going to leave this alone for a second here. Another way to look at this problem, again, this is my area. If we were to think in terms of y, we might notice that this line here is always to the right of this curve. No matter where you draw in a rectangle, we're going to go horizontal rectangles in this case. No matter where you draw in a rectangle, the line is always to the right of the curve. It doesn't matter where you draw it in. And so this is sort of a different way of thinking. We're going to think about turning the rectangles, the Riemann sums, sideways now. And in this case, from 0 on the y-axis up to wherever the top is, looks like 2. So from 0 to 2, the line is always to the right of the curve. Okay, so we could figure out what the area is in terms of y. So let me go show you how we set that up generally. So if let's just draw in a set of axes here. So suppose we have some curve like this. Remember, these don't have to be functions now. So this is maybe x equals g of y. And then over here, maybe we have x equals f of y. All right, and then we're going to go from bottom to top of the region. So we're going to call this bottom value C and the top value D. And so to find this area, so again, so the subregions or the sub the rectangles here, like if you were to draw in Riemann sums, are going to be parallel to the x-axis. And we're trying to find this area. Okay, the area would be given by this integral. Area be equal to the integral from bottom to top, so c to d, and then we would take the rightmost function, f of y, minus g of y, and integrate with respect to y. So very similar to if we were doing top minus bottom, except that we just have a, we look for a function always to, or a curve always to the right of another curve, right? So if we go over here, we can do this in one integral. So the only thing we need to change, though, the only two things, I guess, is we need to change these so they're actually in terms of y. So y equals square root of x. So if this is y equals the square root of x, if we square both sides, then we get this, y squared is equal to x. All right, and then we, for the other one, so we'll take that as this curve here, the leftmost curve. And then we take y equals x minus 2. We move that around, so we'll move the 2 over, so I get x equals y plus 2. That's the rightmost curve. And so then if I want the area of the region R, it's just going to be given by the integral from, and then we're going to go bottom to top, so we'll go 0 to 2. And then we're going to take right minus left, so that's going to be y plus 2 minus y squared. All of that with respect to y, and you end up with 3 1/3 still. Okay? So that is the general process for integrating areas with respect to y, or finding areas between curves with respect to y. All right, let's go do at least one more of these. Like just one more of these. Okay, so for this region, you can see here that we have this curve x equals y squared minus 2 is here. And then we have y equals x cubed, that's just graphed here. And so you can see that if we were to do this top minus bottom, well, first of all, this is not a function, right? That's not a function. That's a curve that fails the vertical line test. This is a function, so that one's fine. But even if we were to break this up somehow and we did top minus bottom, partitioning it would be sort of difficult. We would have to do like, we'd have to cut it right here. And so then we take this top minus bottom here. And then we'd have to do, treat this as the top curve, and then this is the bottom. Well, there's a couple ways that we could find this area, but we would at least have to cut it into two parts. But we can notice with our newfound technique of integrating with respect to y that this curve here, y equals x cubed, is always to the right of this curve here, x equals y squared. And again, you can see, like, no matter where you draw in a horizontal line, the cubic is always to the right of this sideways parabola. Okay? And so again, we're trying to find this entire area here. So what we're going to do is set up an integral in terms of y, and we just have to be careful. This curve here, y equals x cubed, has to be written in terms of y, so that when you cube root both sides, you get x equals y to the 1/3, or cube root of y. This one is already good. And then you just need to find the intersections, and so those are not difficult to compute with a graphing calculator. You end up with these meeting at -1, and this intersection here, this is y, by the way, this is -1 here, and this right here is at positive 1.8. All right, so we're going to integrate from -1 to 1.8. Again, we're doing bottom to top, so -1 to 1.8 here. Really easy to forget that, so try to remember that you are, when you're integrating with respect to y, you're looking at the y-axis for your bounds in the integral. And then we're going to do right minus left, so the rightmost curve is y to the 1/3. Then we're going to subtract the leftmost curve, which is y squared minus 2. That's all with respect to y. All right, drop that in your calculator, and you get a is equal to, I guess this one you could even do by hand probably, but, well, yeah, your calculator is going to be your friend at some point. Anyway, so this is going to be 4.215, okay? And so that's it. Just make sure that you've always got a curve that's to the right of another curve. Make sure that both of your functions or your curves are, your equations are in terms of y, and then finally pay attention to the bounds. Make sure you're doing from the bottom to the top of the region. And that's pretty much it for finding the area between curves.